Today we are going to discuss electromagnetic induction. We will start with magnetic flux. What is magnetic flux? What are positive magnetic flux? What are negative magnetic flux? What are zero magnetic flux? And what is their importance? Then we'll do electromagnetic induction. What are the Faraday's laws of electromagnetic induction? What is the mathematical expression for that? And what is its significance? Then we'll do Lenz Law. What is Lenz Law? And how we can show that it obeys law of conservation of energy. And we'll discuss different cases there where we can apply Lenz Law and find the direction of induced current in those cases there. So all these we'll discuss in today's discussion. We're starting with magnetic flux. What is magnetic flux? It is the number of magnetic lines of forces passing normally through a given area. You have been given an area there. You can find out how many magnetic lines of forces are passing normally to that particular surface or that particular area there. And we can write this one phi as B dot A. B is the magnetic field intensity and this is the vector area there. This you can apply for uniform field. If magnetic field is uniform, then you can apply this one. Or it may be taken phi as B dot dA vector integral of this for non-uniform field. Magnetic field. This we use for the second case when it is not uniform. In fact, if you consider, suppose you have this as the surface and through which we have the magnetic lines of force, or magnetic field is there, which is say in this direction. This is V. And for that, the vector area, if you consider, this is your A. So the angle between the two, if you take it as theta, then that one will give you the magnetic flux passing through this particular area. So if this one has an area A in magnitude and its direction is normal to this one, so vector area, if it is making an angle theta there with the direction of the magnetic field, then we can get the magnetic flux, that is as B dot A. If we assume that this is a uniform magnetic field. Or we can write it as BA cos theta. This is for magnetic flux. Remember, for electric flux also we have taken similar regulation. There it was the number of electric lines of forces passing normally to a given surface. So in that case it was your E dot A. That was the electric flux. And here for magnetic flux we can take it as your phi as B dot A. The unit of this magnetic flux, this is Weber. Or since it is a dot product of your magnetic field intensity and vector area, so we can also take it as Tesla meter square, because Tesla will be the unit for magnetic field intensity and area unit we can take it as meter square. So in that case, you have Weber or Tesla meter square. That is the unit for magnetic flux. Magnetic flux we can classify in three categories. One is taken as the positive magnetic flux, another is the negative magnetic flux, and the third one is zero magnetic flux. Now it is basically depending upon how the magnetic flux is meeting a particular area there or it is coming out from particular area there. This will basically give you whether the magnetic lines of forces are coming out of a surface or it is entering into the surface or it is just grazing the surface. So if you consider the expression for this one, phi, it was your B dot A, which is your BA cos theta. Now you can see as this cos theta term depends upon the angle there, and its value will be there depending upon the value of theta. It may be positive, it may be negative, or it may be even 0. So we can get different values there from cos theta. It may be positive, it may be negative, it may be 0. So with that, we take the flux also related. So if you consider magnetic flux as positive, so positive magnetic flux, this we get when the magnetic field intensity makes acute angle with the direction of vector area. So if here, if theta is acute, then cos theta will be positive. So in that case, the flux will be positive. So we say that one it as a positive magnetic flux. What we will get here, suppose this is your field and this is suppose your direction of the vector area. This is the direction of the magnetic field. This angle is theta. This is an acute one. So in that case, it is representing magnetic lines of forces which will be positive there, because this cos theta value will be positive here. One more thing you can notice, these are like representing magnetic lines of forces which is coming out of the surface. So outgoing flux will be taken as positive magnetic flux, because magnetic lines of forces will be coming out of the surface. Then only the angle between the two will be acute. So if the angle between vector area and magnetic field is acute, then we get positive magnetic flux. And these will represent magnetic lines of forces which is coming out of the surface. So they will be the positive magnetic flux. Similarly, if you take the negative magnetic flux, here, if suppose we assume that the angle between vector area and magnetic field is obtuse, in that case what will happen? The magnetic flux will become negative because cos theta term will become negative. So if theta is obtuse, in that case cos theta term will be negative. So phi value will be negative. And in that case, we can say that the magnetic flux will be negative. So how it will be related there? If suppose this is your vector area, and suppose the magnetic field is in this direction, this is your V. This particular angle is the angle between the vector area and magnetic field. This is an obtuse angle. So in that case, this one will represent magnetic lines of forces which are negative. And these are what type of lines of forces? They are the one which is entering inside the magnetic. These are the representing the magnetic lines of forces which are entering a particular area. So as outgoing flux was positive, incoming flux, that will be taken as the negative one. So here, incoming flux, they will be taken as negative magnetic flux. So in that case, they will be taken as the negative because they are just entering into the given area there. So this is the positive magnetic flux and negative magnetic flux. Similarly, for zero magnetic flux, this will get when the angle between vector area and magnetic field is 90. So if theta is pi by 2, then cos theta term will be 0. And in that case, the flux will be 0. So in this case, no magnetic lines of forces will be coming out of the particular area there. So suppose you have any area like this. This is suppose representing normal area. And magnetic field, if suppose it is entering there in perpendicular direction to that, this is suppose the direction of the magnetic field, and this angle is 90. In that case, that particular value of the magnetic flux will be G. It is just like the magnetic lines of forces will be just grazing the surface. Like suppose if I assume that the plane of the board we are taking as the given area there. So vector area of this one will be perpendicular to this one. It will be either coming out or it is going into the plane of the board. And if suppose the magnetic field is from left to right, so these are representing the magnetic lines of forces there, which will be grazing this particular surface. They are not going into or it is coming out of that. So in that case, the magnetic flux will be 0 there, because they are actually not coming out of the surface or given area there, or neither they are entering into it. So in that case, that magnetic flux will be taken as the 0 magnetic flux. So if the angle between the two is 90, it is 0 magnetic flux. Let's start with electromagnetic induction. Electromagnetic induction is the phenomena in which there is an EMF generated or a current is induced in a closed circuit of loop whenever magnetic flux linked with it changes with time. You have any closed loop there or any closed circuit is there, and suppose if the magnetic flux linked with that is changing with time, in that case there will be a current induced in the closed circuit, or that phenomena we call it as the electromagnetic induction. This has also been noticed that this type of change will be there only when that flux is changing. The moment that change of the flux is stopped, or there is no longer change of the magnetic flux, this current which is induced or current which is developed, that will become G. So in this phenomena, basically, the current which is getting developed, that we call it as the induced current. Similarly, the corresponding EMF which is generated, that is called as the induced EMF. And the phenomena itself is called as the electromagnetic induction. Now, how you can have the change of the flux? If you consider phi, which we have represented as your B dot A. So this is your BA cos theta. So this is your magnetic flux. If you want to know that how we can change this flux, because along with the change of the magnetic flux, there will be induced current developed there in the closed circuit. So we can change magnetic field, we can change area of the loop, we can change theta. If any of these or more than the one is changed, there will be EMF developed in the circuit, or the induced current will be developed in the circuit. So we get this electromagnetic induction from there. Now, how you can change B? If suppose you have magnetic field being produced due to a magnet. Suppose you have a magnet here. This is suppose the magnet, this is North Pole, South Pole. This is a loop, or maybe a coil is there. If we are moving the magnet towards the coil, or we are moving it away from the coil, then the magnetic lines of forces passing through it will change. As you are approaching or making this magnet approach this particular coil there, in that case lines of forces will go on increasing. Because the magnetic lines of forces we can show that it is say coming out of this one. So as we are suppose moving this one closer to it, then the more and more lines of forces will pass through this one. So magnetic lines of forces is increasing there. Basically, there is a change. Similarly, if you are moving this magnet away, again there is a change of the magnetic flux, because now lesser and lesser number of magnetic lines of force will pass through them, because you are moving this one away. Similarly, you can keep this magnet constant or fixed at a particular position. You can move the coil towards it. Then also, at the position of the coil, magnetic field value will change. And if the magnetic field value is changing, obviously the magnetic flux linked with that will also change. Because magnetic flux will be given by B into A. If B is changing, in that case, definitely the flux will change. So if you are moving coil towards the stationary magnet, then it is changing. You can move the coil away from that, again it will change. You can move both, either towards or away from one another. In that case, again, there will be EMF generated or the flux will change. So here there will be induced current developed. So this is when we are changing magnetic field. This is when we are changing that magnetic field which is produced due to a magnet. It may be magnetic field is produced due to current carrying conductor. Suppose this is the loop and there is a current flowing through a wire. If the current value is changing, in that case magnetic field at different points will also change. So if this coil is stationary and if the current is suppose increasing there or decreasing, flux linked with this one will change. So in that case also we can get the EMF generated or induced current developed. Also, if suppose you take any particular loop whose area is changing, if you have a loop and you are changing its area there, in that case also magnetic flux value will change. So if the magnetic flux value is changing, definitely induced EMF will be generated there. Or theta is changing. Theta is the angle between the magnetic field and vector area. If you are changing the orientation of the coil, in that case you are basically changing the angle between the two. So if orientation of the coil is changed, definitely the flux will also change. This is the basic principle behind the design of the AC generator. We move a coil there in the magnetic field, and if you are rotating that coil there, then there is EMF developed or the current is induced in that coil. And that is what we are taking in the output there. So there can be change of the magnetic flux due to any reason there. And whenever there is a change of the magnetic flux, there will be induced current developed in the closed circuit. Or Faraday has given two laws there on electromagnetic induction. First law is much more like the definition of the electromagnetic induction. So this is that whenever magnetic flux linked with a closed circuit or loop changes with time and EMF is developed in it. You have a particular coil or closed circuit there or a loop. Whenever magnetic flux linked with that is changing with time, there will be an EMF induced in it. And this will last only as long as the flux is changing. So in that case, we get this first law stated there, that EMF will be developed in the closed circuit or loop whenever magnetic flux linked with it is changing with time. Second law is where it gives the magnitude of the EMF which is induced or developed there. That says that the magnitude of the induced EMF developed is directly proportional to rate of change of the magnetic flux associated with the closed circuit or loop. So this EMF which is developed or induced, magnitude of that is proportional to rate of change of the magnetic flux. So if we take E as the magnitude of E as the EMF induced, so its magnitude is proportional to rate of change of the flux, or we can write E equals to K d phi by dt, where K is a proportionality constant. If the terms are so defined that K is 1, so if we have K is 1, that means we are defining the term in such a way that the K value is 1. In that case, this E will be equals to d phi by dt. So magnitude of the EMF induced will be directly proportional to rate of change of the flux. So this is the statement there given by the second law. What is the mathematical expression which we get from the second law? Remember, this is the magnitude. If you apply Lenz law, so applying Lenz law, to this, we get expression which is your E minus d phi by dt. This negative sign is in accordance with Lenz law. So this negative sign will be due to the Lenz law. Mathematical expression, if you take, given by the Faraday as the second law, that is just that is the E means magnitude of E, you can say. This is proportional to rate of change of flux, so E is equals to d phi by dt. And when you take this Lenz law applied to that one, then it is written as E equals to minus d phi by dt. And this negative sign is basically, this is due to Lenz law, and it will be indicating that it will be in such a direction that it will oppose the cause which is producing it. So it is basically related with the direction there of the induced current which is developed there. Lenz law says the direction of the induced current in a closed circuit or loop is such as to oppose the cause producing it. Or you can say that the induced EMF developed in the closed circuit or loop will be such as to send the current in the closed circuit or loop to oppose the cause which is producing it. So if the magnetic flux is increasing, it will try to decrease it. If the magnetic flux is decreasing, it will try to increase it. So it is in such a direction that it will be opposing the cause which is producing it. So let's take the different cases there, then it will be more clear there how we can apply that to the different cases there. But first of all, just try to understand that Lenz law is in accordance with law of conservation of energy. So this obeys law of conservation of energy, or this is a consequence of law of conservation of energy there. So it is a consequence of law of conservation of energy. Let's see how we apply that, or how we are using that. Suppose we take one case that we have a certain region in which we have the magnetic field. Suppose the magnetic field is directed into the plane. So B represents the magnetic field. And in this region, we have a parallel track. These are the two conducting wires there, or track, you can understand. And this is connected by a conducting wire here. So we have this one as a A, B, C, D, as a, you can say, U-shaped track there, made of conductor, on which we have a slider. So this PQ represents a slider which is kept over this parallel tracks A, B, and C, D. It can easily slide over this one. Now, suppose we take this one, that it is at some distance. Let it be that it is at a distance x. This length is L. Here, area enclosed, that will be given as your L into x. So this is the particular area there enclosed. Magnetic field is B. So I can find out what is the magnetic lines of forces associated with this. And that will be your B into L into x. Suppose we move this slider towards right. That means we are just pushing this slider towards right, so that in a short interval of time, it reaches the point P dash, Q dash. So it is going to the point P dash and Q dash. Now you can see that with respect to the earlier one, this area was initially L into x. Now this additional distance will be there. Suppose this distance is your delta x. So the new area will be your L into x plus delta x. Or what we can just say that this area enclosed will increase. If the area enclosed is increasing, what will happen to the magnetic flux? That will also increase. So if the magnetic flux linked with this one is increasing, according to this Faraday's there will be electromagnetic induced current developed there. Or whenever, now as the flux is changing, there will be current induced in it due to electromagnetic induction. And if you want to find the direction of the current there, as the slider will move towards right, there will be increase in the area enclosed. As the area enclosed is increasing, so magnetic flux will increase. So there will be current induced in the circuit because the magnetic flux linked with this is changing with time. Now, direction of this one, as per the Lenz law, should be to oppose the cause which is producing it. It should be in such a direction to oppose the cause which is producing it. So magnetic flux is increasing. Magnetic lines of forces is into the plane. So to decrease that magnetic flux, it should set up a magnetic field in opposite direction to that. Because only if it has the field produced in a direction opposite to that, the flux which is increasing can be decreased. Because here you can see area is increasing. So to keep this magnetic flux either same or to decrease that, this B should decrease. And how it can decrease B? B, which is the external field already acting into the plane. So it can decrease it if it set up a current in such a direction that the field produced by that is in opposite direction to that. So that is possible if it is flowing in the anti-clockwise direction, so that the field produced by that will be in out of the plane direction. And if it is in out of the plane direction, in that case, the current there will be in the direction Q to P, as it is anti-clockwise. So from the in the slider PQ, it will be flowing in a direction Q to P. So this is as per the Lenz law. Now we are assuming that the direction which is indicated or suggested by Lenz is not correct. Let's assume that it is in opposite direction to that. So in that case, we assume that this current which is flowing in this closed loop is not in the direction what is shown by or given by the Lenz, but it is in opposite direction to that. So actual direction indicated is your Q to P. We are assuming that it is in a direction opposite to that, so it is P to Q. Now, if I assume that the current is in a direction P to Q, magnetic field is directed into the plane. So in that case, if you consider the force which is experienced by this slider, as per this, it will be in which direction? You can apply Fleming's left-hand rule there. Current is downward, say P to Q. Magnetic field is directed into the plane. Current is in a direction P to Q. So that means it is downward there. Magnetic field is directed into the plane. So force will be in a direction which will be towards right. That is the direction in which we have pushed the slider initially. So the force on the slider will be towards right. Now, if the force on the slider is towards right, in that case, it will have an accelerated motion, because if the force is there, there will be acceleration. And if acceleration is there, then this slider will move with greater and greater velocity. If it is moving with greater and greater velocity, in that case, the rate of change of the flux, which was basically your E d phi by dt, this one will go on increasing, because the time duration will be now lesser and lesser with the passage of the time for the same distance which is being moved here, because it has an accelerated motion there. So in that case, this slider will move with greater and greater velocity or the force there, because if the force is increasing, what will happen to the current? Force is your ILB. There will be force. It will have an accelerated motion. Due to that accelerated motion, this EMF will increase, because rate of the change of the flux is increasing, so EMF will increase. If EMF increases, the current will further increase. That means this current is increasing further. And if this current increases, the force will also increase further. Remember, even if the slider would have moved with constant force, then also it had accelerated motion. Rate of change of the flux would have increased at a very rapid rate. But here, the force is not constant. It is also increasing. So this slider will move with greater and greater velocity without any expense of energies or without any amount of energy supplied to it. What we have done, we have only initially pushed this slider there, and then it is now moving with greater and greater velocity. So this is violating law of conservation of energy, because in this case, you are getting energy generated there without any supply of energy. So you are creating energy there, or it will be violating law of conservation of energy. You can treat it in this way also. Suppose these two parallel tracks which we are showing, these are the tracks of the train. And this P which we are taking, it is the vertical component of the Earth's magnetic field. You have one compartment of the train there. So along with the axle of the wheels there, it is forming closed loop there. And now suppose if I just push the compartment there, in that case, there will be change there. So induced current will be developed there in the circuit. And as the induced current is developed, in that case, if we assume that this direction is not correct, what is shown by the Lenz, in that case, what will happen? There will be force developed on the axle of the train there. So it will move with greater and greater force there. And remember that as this axle is experiencing force and the compartment is moving, this is moving without any engine there. So without any supply of the energy, you are moving that, you have that compartment moving there, and that is moving forever. So this will violate law of conservation of energy. That means the direction which we have assumed for the flow of the current is wrong, because this direction of the flow of current from P to Q is violating law of conservation of energy. So this is not correct. That means the direction which is suggested by Lenz is the correct direction of flow of current there. So this is why we say that Lenz law obeys law of conservation of energy, or it is a consequence of law of conservation of energy. Another example we can take where we can show that Lenz law is obeyed. Let's suppose you have a solenoid and we are bending it in the shape of a circle there. We are framing some sort of a toroid, you can say. So if you have that, so suppose we take, this is some sort of a toroid there. Here, along with its axis, suppose we put a non-conducting material there, and we fix a magnet with this one. You have a magnet, and what we do, we tie that magnet with a small ring so that it can slide over this particular ring which we have put. So now suppose I drop this magnet from any position so that it slides along with this ring there. So what will happen? The magnetic flux linked with the loop will change, or the coils will change there. As it will change due to Lenz law, it will suggest that the change which is there will develop a current which will try to oppose the cause which is producing it. So induced current should be in such a direction to oppose the cause which is producing the change of the flux. And why this flux is changing? Because of the movement of this magnet. So it should oppose this movement. That means it will set up the current in such a direction that it will produce a north pole there, and in that case there is repulsion, so it will be opposed. But if I assume that the direction which is suggested by the Lenz is not correct, let the current be in opposite direction. So for that, it should flow, current should flow in opposite direction. That means say it is in the clockwise direction in this loop. And if it is clockwise, then it will be the south pole developed here, it is north pole. So instead of opposing the motion of the magnet, it will support its motion. That means it will pull this magnet towards it. So there is a force of attraction. If the force of attraction is there, magnet is being pulled In that case, it will move with faster rate. So this magnet will move at faster rate, and in that case, there will be change of the flux there, changing at a very rapid rate. So as it is changing with a very rapid rate there, in that case, there will be EMF developed, which is increasing in magnitude. If the EMF is increasing in magnitude, there will be the current also increasing in magnitude. So this magnet will move forever, and it will generate current there in the circuit, which is increasing in magnitude. So you will be getting their current generated here in the circuit, suppose, and this will act as some sort of your generator. So it is generating electricity out of nothing. You have just dropped the magnet and it is generating electricity. Obviously, it will violate law of conservation of energy. This is the reason why we say that the direction which we have assumed, which is opposite to the direction suggested by Lenz, is not the correct one. As a result, whatever it is suggested by Lenz must be the correct one, and it obeys law of conservation of energy. To understand Lenz law application there to the different problems there, and to predict the direction of the induced current there in the closed circuit or two, let's take few cases there. Suppose you have a coil here, and here we have a magnet. This is the north pole, this is the south pole, and we are moving the magnet towards it along its axis. If you are moving the magnet towards this coil, and in that case, the magnetic flux linked with this one will change. It will increase there. As it is increasing, it will try to set up current in the circuit which will oppose this motion of the magnet. So for that, it should set up a field in opposite direction to whatever is produced by this magnet. Magnet field will be from left to right. So in that case, it should set up field in opposite direction. So we can assume that if the current is there, say in the anti-clockwise direction in this loop, in that case, this will set up a magnetic field which will direct it in this direction, say from right to left. So the direction of the induced current there will be in this direction. That is, in this loop, it is anti-clockwise, so that magnetic field is directed from right to left. So in this case, the current is anti-clockwise. Just other case you can consider. Here, this is the magnet, and now this time we are moving it away. If the magnet is being moved away, in that case, what will happen? Magnetic lines of forces will decrease. As the magnetic lines of forces are decreased, in that case, it will try to increase it. How it can increase it? Just by pulling it magnet back towards this coil. So for that, it should set up the current there. That it should set up the current in the clockwise direction. Because if it is setting the current in the clockwise direction there, the magnetic field will be in this direction from left to right. The field due to this magnet was also from left to right. But as this magnet is being pulled away, the magnetic lines of forces were decreasing. So to compensate that, it should set up field in the same direction. So it should be in the clockwise direction. So this is your clockwise. So that is the direction of the induced current there in this. Now here, remember one more thing there, that if you consider that it is in the anti-clockwise direction, so it is like this, the anti-clockwise direction. Thumb is indicating direction of magnetic field. So this is the direction of the magnetic field, and magnetic lines of forces, we assume that it is originating from north pole. So we can assume that this side we have the north pole, this side we have the south pole there. So that means this will be the north pole developed here if it is flowing in anti-clockwise direction. And with that also you can explain, as the magnet is moving towards it, it is the north pole approaching this coil. If the north pole is developed here, there will be repulsion. It will try to oppose its motion. So this will oppose the motion of the magnet towards it by setting up a north pole here. And this will be there only if the current is flowing in the anti-clockwise direction. For other case, if the magnet is moved away, current, suppose we take it is in the clockwise direction. So if the current is in the clockwise direction, it is the south pole facing this side. So in that case, this will be the south pole developed here. And if the south pole is here, if the magnet is moved away, it will try to attract it. So it can oppose the motion of the magnet away from this one. So this way also you can understand that how the current should be in the clockwise or anti-clockwise direction there if the magnet is moved. Suppose we take another case. We have a ring, metallic ring is there. Say it is a copper and is kept horizontally there, suspended in a air. And there is a magnet which is being dropped. And it is falling along its axis. If it is falling along its axis, it is asked what is the direction of the induced current there. That we can easily say. If it is the direction the induced current is required as the north pole is approaching it, in that case it should set up a north pole here. So for that it should flow in the anti-clockwise direction. So in that case the current will be in the anti-clockwise direction. But if it is asked if the magnet is dropped freely, and suppose A is the acceleration of the magnet, then what will be the acceleration of the magnet? This is equal to G. Second, it is less than G. Third, it is greater than G. And fourth, it is less than G when magnet is above and greater than G when it is below. So in that case, you have to find what is the acceleration of this particular magnet. Now, as it is falling, there will be induced current developed in this loop. And as the induced current is developed, it will try to oppose its motion. So obviously, this one will not have the acceleration same as acceleration due to gravity. So this is not correct. As it is falling, there will be opposition to its motion. And due to that, its acceleration should be less than G. So this is the possible one. But is it here north pole is approaching it? And once it crosses it, in that case, the north pole will be moving away. So is it always A less than G, or it is A greater than G when it is below? Remember, when it is falling, as long as it is above, it is the north pole approaching it. So obviously, it will set up a current there so as to oppose that. But the moment it crosses, now it is the south pole which is nearer to this one. So it is moving away. So it will try to attract that one, because now the south pole is moving away, or the magnet is moving away from that. So it will set up the current in such a direction to oppose the motion of that magnet. So as it is moving away, it will try to attract it. As it will try to attract, definitely this time again the acceleration will be less than G. So this is the correct option for both the cases, whether it is above or it is below. So all along its motion, acceleration will be less than acceleration due to gravity. Suppose we take another case. This time again we have a metallic ring, but with a small cut. And if now it is being dropped, again a magnet is being dropped along its axis, and it is asked what is the acceleration of this magnet, whether it is equal to G, less than G, greater than G, or this case. So remember, when the magnet is dropped, in that case, what will happen? Here, this is not a closed loop. There is a small cut. So as there is a small cut there, so induced current will not be set up. So its motion will not be opposed there. And as the motion is not opposed, in that case, it will fall with acceleration due to gravity. You can take it in this way also, as this is having a small cut. So magnetic flux is not only in this part, even the flux which is outside, they are also the part of the system, because it is not a closed loop or closed circuit there. So obviously the flux is not changing. In that case, there will be no induced current and no opposition will be there. So it will be A equal to G. Let's take one more case. Suppose you have a ring and this is the wire through which the current is flowing. If it is asked what will happen to the direction of the current developed in this loop, what is the direction? So if it is just said that the current is flowing there, be very careful when you are reading the question. If it is just shown the current flowing in one direction, say left to right or right to left, and if it is just said that current I is there, it is not mentioned whether the current is changing or not. If nothing is mentioned, we'll assume that the current is constant. And if the current is constant, magnetic field at the position of the loop will be fixed. Magnetic flux will be fixed. It is not changing with time, so there is no induced current. So in that case, there is no induced current. Because if it is not mentioned whether it is changing or not. So if it is your constant, in that case, there is no induced current. If suppose we assume that we have a metallic ring or a loop is there, and there is a wire through which the current is flowing from left to right and it is increasing. So here, if the magnetic field current is increasing, magnetic field due to it at the position of this ring or loop will also increase. Magnetic field due to this one will be out of the plane. As it is out of the plane, in that case, what will happen? Their flux is increasing. So to decrease that, the current should flow in this loop in such a direction that it produces field in opposite direction. So then it should flow in the clockwise direction. So that if the current is clockwise, magnetic field is directed into the plane, which can decrease the flux which is increasing here due to the increasing current. So the direction of the induced current will be clockwise. This will be clockwise in this case. So that field is directed into the plane. Whereas if suppose the current is flowing again left to right, it is decreasing now. If it is decreasing, in that case the field, of course it is still out of the plane, but it is decreasing. So for that, it should set up the current in the loop so that it can compensate for the decrease. So it should set up the field in the same direction. So for that, if it is setting the current in anti-clockwise direction, in that case it will be in the that same direction as the field due to this current, and it can compensate for decrease of the magnetic flux. So this current should be anti-clockwise. So the current in this one should be anti-clockwise, so that if it is anti-clockwise, it is coming out of the field. So this type of examples you can get there, or cases you can get. You will have to just see that what happens to the magnetic flux. Is it increasing or decreasing? If it is increasing, the direction of the induced current should be such to decrease that. And if it is decreasing, it should be in a direction to compensate for that. So it should try to increase that one. So if you just take it that in that mind, you can easily get the correct direction of the induced current in any circuit or